Okay, the next section 9.5 is on series. So we'll do some summation notation, we'll add up arithmetic and geometric sequences, and we'll find infinite series as well, if they converge, that is, for geometric. And infinite series are basically the fundamental concept of integral calculus that will help you understand calculus, hopefully. So here's summation notation. Technically K is called the index of summation. I probably won't use that term very much, but we will do some examples. If we're adding the sum of a finite arithmetic sequence, we have a formula for that I put on the formula sheet. It's right here. So here's an example then. Consider the sequence. This is supposed to be like dot, dot, dot right here. So we're starting with 1. So this is arithmetic. We're starting with 1, so that means the first term is 1. The common difference is what I'm adding each time, which is also 1. So if I want to find an explicit rule for the sum of the series, then I'm adding up the terms from n equals 1 to n. So let me use a different variable then. Let's use k here then. And I need to put the sequence right here. Now the sequence is a sub n equals the first term plus n minus 1 times the common difference. So the first term is 1 plus n minus 1 times the common difference of 1. All right, I can simplify this. This just is n. So instead of using n, though, I used k here. So I'm going to do k. So here's my summation notation. Now I can write this out with a formula as well that we just had. The formula for this is n times the first term plus the last term divided by 2. So the first term is 1. I'm sorry, the number of terms here in this case is n times the first term is 1 plus the last term is also n all over 2. So this is what they're looking for part A, which is a little confusing, but for part B then they're just asking us to add up the first 100 terms. To add up the first 100 terms, then we're actually putting in 100 here. And so you can put in 100 here as well to solve it. But if you do that, you'll get the answer, which is 50/50. Now I'm going to show you how to do this in the calculator real quick. This is something you can do. I show you in the homework as well. If you go to alpha window and do summation, you're going from k equals 1, I'll use x here for my variable, to 100 of the same variable k, or x in this case. Hit enter and you'll get 50/50. Okay, here's another example then. It says the corner section of the stadium has 6 seats along the front row. That basically told us the first term is 6 for our sequence. And each successive row has 3 more seats. So it'd be second term would be 9, third term would be 12, and so on. So this is an arithmetic sequence. Let's just write the rule for the sequence, which is the first term plus n minus 1 times the common difference. So the first term is 6, and then the common difference is 3. So there's my rule. I can simplify that if I wanted to. It says if the top row has 24 seats, so that's saying eventually we're going to end up with 24 seats at some value. How many seats in the entire section? What they're asking for then is for us to add up the first 24 rows. So we would go from, or the first n, so we'd go from n equals 1 to this highest value up here, which we don't know what that is. We can find that of this sequence right here, which I'll simplify this. This is 3n and then plus 3. So what we need to do is find out what term number this 24 is. For that, what we can do is plug in 24 here and solve this. So this is really 24 equals 3n plus 3. Subtract 3, you get 21 equals 3n, so n is 7. So that means that this is the 7th row. I should have put a dot, dot, dot right here. So we're adding up the first 7 rows, or the first 7 terms of this arithmetic sequence from 1 to 7. You can do that in your calculator like I just did, or you can use the formula, which is n times the first term plus the last term all divided by 2. So there's 7 terms. The first term is 6. The last term is 24, and divided by 2. That gives you your answer of 105 total seats. Now next we're going to talk about the sum of finite geometric sequences. We have a different formula for that right here that we're going to use. It's on the formula sheet. We can also do infinite series right here. In order to do infinite series, we're going to use this formula right here. But there's a stipulation, and that stipulation is that our ratio has to be a number between -1 and 1. And that's what this says right here. Right, so I put that in the formula sheet as well. But it's only going to work when our infinite geometric series converge. So what that means is when we're multiplying by a number that's making each successive number smaller. So here's an example then. Determine whether the series converges. If it converges, give the sum. Well, our ratio is right here. If you look at, this is g sub n equals the first term times the common ratio to the n minus 1, or they're using k in this case, which is fine. You can use whatever variable you want. Our ratio is right here, which is 1/4. So because our r is 1/4, it does converge because that's a number between -1 and 1. So we can use the formula, which is the first term over 1 minus r. The first term is, this case, when we plug in 1, we get 2 as the first term. And then the ratio is 1/4 like we talked about. So that simplifies to 2 over 3/4. So let's multiply by 4/3 instead of divide by 3/4, and we get 8/3. So our answer is 8/3 for the sum of those infinite number of terms of that geometric sequence. Okay, we'll do a bunch more problems in the homework help, and hopefully it'll make more sense.